do like to claim to be a geologist. So actually that's important because when I talked to Greg about preparing for this presentation, he asked me to more speak to explorers than to speak to geophysicists, and I think that's important as the theme we're trying to do here is advance better effective use of geophysics in exploration. So I'm going to attempt to do that. My main aim here is really to promote to explorers what we believe is the most important advance in geophysics in the last 10 years, and that's 3D Earth modeling of geophysical data. Now, the business of 3D Earth modeling of geophysical data is just represented by that little cartoon you see. It's the ability to take geophysical measurements and mathematically convert those into reasonable and realistic models of physical properties of the Earth, 3D models that we can then use in our exploration projects. We believe this is so important that 3D Earth modeling should really be applied to every exploration project that has geophysical data. Although the techniques have been around for about 10 years and the development of them has advanced a lot in 10 years, they're still only applied to a small fraction of exploration projects. And that's because of what we think of as three challenges for that. The first is complexity. These techniques are very complicated to use. They're complicated to set up. You have to do a lot of things with your data to get them ready to work with a 3D inversion, 3D modeling system. So that's been one of the things that we wanted to have a look at. The second is that all of us have one of these things, or something that looks like one of these things, and the main tool of an explorer is something like a laptop or a PC, perhaps something more powerful. But to do 3D inversions, you actually need a lot of horsepower. And so the people that are doing 3D modeling, 3D inversions today actually have either one or two or three or five big computers that they're able to apply to the problems. And they have a lot of patience because it takes a lot of time to make those happen. The third challenge is knowledge, really, and how we're going to share and learn and get better at applying these techniques to be effective in exploration. And there's a lot to learn as you do these things, and we really believe we're only going to be able to do that if we can just get better at sharing what we're able to learn among each other. 3 years ago, Rob Ellis joined us, and Rob is an expert in 3D Earth modeling. And we really sat down and thought about these challenges and spent 3 years to really address these. So I want to show you how we did that. The second part, of course, you saw in the title for this talk, it's about the cloud. So as my computer science side of me also feels the most important advance in the last 5 years has been the development of cloud technologies that we can start to use for exploration. Now, cloud to us, or one thing people often ask is, well, what is the cloud? Cloud to us is really anything you can do on the internet that creates value for you. That includes looking for data, collaboration with others using things like Basecamp. Your email is a cloud application, Office 365, Google Docs, all the kinds of things you see up here. There's also exploration data services like Geosoft app and things like that. If you can hook up to the internet and it does something for you, as far as we're concerned, that's a cloud application. And what we've done is thought about how we can use the cloud to put VOXI in the cloud. VOXI is our 3D Earth modeling system that runs in the cloud. So let's think about this from an exploration perspective. About, I guess, a month ago, Peter Cashin, an old colleague of mine, came to me from Quest Rare Earths. I actually didn't know it was Quest Rare Minerals at the time. I think we had uranium in the card that I saw. And the basic exploration problem he asked me is, Ian, what's this? And that's a typical, simple question that's asked of geophysicists all the time. I didn't know very much about what it was. I just asked Peter, where are you in the world? He said he was working in northern Quebec. As an old greenstone geologist myself, I'm used to Archean rocks. I know Canadian Archean rocks are highly deformed. There's very little that could ever be perfectly circular in an Archean environment. I learned a little bit about rare earths and even more watching your talk, John. But when Peter asked me what this was, my first reaction would be, and I'm pretty sure some of you out there also think, well, it must be a meteorite impact. You can't get something that perfectly circular in really deformed Archean rock. But anyway, so I set on a mission to finding out what that is. So here we go. The mission starts. So by the way, when you're looking at these slides, you'll see a little cloud every now and then. When I show that cloud in the top right corner, that means I've used the cloud service. In this case, we're using the Bing Map service, and we're now able to bring that into the software, just drop it on our maps with us. So I've used Bing Maps, and we're going to just zoom in on the area that we're interested in. It's up in northern Quebec, near Labrador. I've put Voisey's Bay on here just for reference, because we all know where that is. Now at this point, it's winter time, so it's all snow, and we're all now used to having a look at the satellite data. So this is the Bing Map satellite data. Again, the cloud in the corner. We can just turn that on now, pull it down from the cloud, and apply that to our exploration project. Yes, that shows us a little more information. As explorers, we're interested in really, a starting point is often geology. This is the Canadian regional geology map that's also available. And I'm going to, as a geophysicist, I love looking at this stuff. This is the regional total magnetic field data that's been pulled down from the GSC DAP survey. So I was able to pull that down and start to look at it. And now we start to see much more texture and have a sense of the magnetic properties of the rock that underlie that geology you just saw. Let's zoom in a little bit more. Now as I come into this area, you can see Voisey's Bay there in that white circle at the top. And you can see these old Archean rocks coming down. This is the deformed rocks I was talking about earlier. But you can also see some now, some younger, it turns out, Proterozoic intrusions, which are a good billion years younger than the rocks that intrude, showing up here. So this Voisey's Bay is here, and you can sort of make out an outline of a demagnetized, sort of intrusive zone here. But I'd like to draw your attention to similar sorts of features intruding on these and distorting these rocks over here and up here. Now these are Proterozoic perk alkaline intrusions, and it turns out that the reason that Quest Rare Earths is there is this particular deposit, Strange Lake, has been working on really for 20 years. That's what brought them here, and it's a pretty well advanced development now to become a mine. And a rare earth mine, and it's obviously on the northern edge of this little intrusive thing up here. While they were doing this, they did go out and do some regional grabbing of boulder samples down here, and I want to draw your attention to this particular deposit, Misery Lake, down at the bottom. Zoom in on that a bit. Now this is the course data that I downloaded from the GSC, and this is where they picked up some interesting samples, and they just wanted to have a closer look at this. And they contracted an airborne geophysical survey to have a look at this mag and magnetics. So I'm looking at the magnetics now. And this is that original thing that Peter threw at me. Said, "What's this?" So by now, I'm a satellite impact skeptic. I realize this is really a zone intrusion that has a magnetite-rich zone in it, and that circle is caused by where this thing is cut off by the current erosional layer. Okay, let me think about this in 3D. For most geophysical projects, people would take this map, throw it on top of all the stuff that they're doing, and do the best they can with it. Only a few projects will then try to produce a 3D thing from this. So let's talk about that a bit. So back to the simple thing that Peter gave me originally. Again, I'm going to use the cloud. Something that I find very useful now is to always bring the satellite data and have a look at it. So this lake is Misery Lake. It's in the center of this circle. You can actually see a circular outcrop ring around this, so I know it has a surface expression. There's a resistive layer that's part of that zoning that we can see on the surface. Okay, let's go into the third dimension now. One thing thing I do like to do with geophysical data is show it in 3 dimensions, plotted against itself in 3D. I find when people look at magnetic maps, they're always asking me, what are the reds and what are the blues? And I say, well, the reds are the high and the blues are the low. When I show it this way, it's really clear. And not only that, it's interesting that what looks like just a simple ring in 2D, you can actually see there's quite a bit of magnetic relief in this. So it gives you another dimension on the data that isn't necessarily obvious in 2D. Let's pull this back and to the original question and ask ourselves what's going on under the Earth that caused that anomaly. So this is how it works. With VOXI, you display your data in map view, and you draw a polygon around the thing that you want to model, and you pose that question. Give me a model of what's going on here in 3 dimensions. What VOXI does then is it creates a 3-dimensional mesh underneath the Earth automatically based on the size of what it is that you've asked for, and a few other parameters. You notice the cloud was brought to bear here. What I did is I pulled down the digital elevation model from the Geosoft VOXI server, which is another cloud service that I can get global DEM data anytime that I need it. So I pulled that in and put it in here, and VOXI has automatically cut this surface off at that surface layer to create the model problem that I want to work with. Next, I bring in the magnetic field data that I wish to model, and it will bring that in, and it will draw it over the model where it was measured, I think 90 meters above the ground in this case. So let's have a look at this in the software. And this is what it would actually look like in the software. And I'm going to draw your attention to this this green button up here. This is when the magic starts happening with the cloud. When I click that, a panel will open up at the bottom, and we'll connect to a cloud server. Now, this is what the cloud actually looks like. This particular server is a Microsoft server just outside Chicago. This building houses or has the potential to house 3 million cores, and that's the thing that we're going to run this problem on. So this is the system that's available to all of us simply by hooking up our internet connection. Once we've hooked up and created a secure connection, we then upload the data that's required for this particular model to that server. That upload happens over a triple secure network. It's secure because we compress and stream the data in a binary format that only VOXI could understand what it is in the first place. We then encrypt that ourselves, and then we rely on HTTPS encryption. So there's 2 encryptions on top of this. And the data moves from behind your firewall to behind our firewall in the cloud. So there's no way that data can be seen by anybody except behind your firewall and behind the other firewall. Now once it's up there, this is what that thing actually looks like inside one of the data centers that are inside of there. And what we'll do is, based on the size of your model, we start to spin up cores. So depending on how big your model is, we calculate how many cores are required. We spin them up just to run that particular project, and then we set them to work, and they solve the problem for us. And then afterwards, the solution is then downloaded to the PC. So the idea is that this can be done from that simple laptop that I showed you earlier. You don't need the big computer. This is your big computer. So let's look at what the solution looks like in this case. That was the problem we posed. And what the server gave back to us is a 3D block model, if you like, of the magnetic susceptibility of the rock that explains correctly that particular anomaly. I won't get into the fact that there's many different possibilities that will explain that anomaly, but this particular model will produce exactly that anomaly that was observed. I'm going to peel this back now so you can actually see the magnetic, the stronger magnetic parts of this that look more geologically reasonable for what we're looking at. I'll tilt it up. Now, one of the learnings we had from doing this modeling is it actually shows two zones. There's an outer ring and an inner ring, and of course this piece in the middle is causing the big anomaly. And you can see these things going on here. And Quest actually, before looking at this modeling, they did a little bit of exploratory drilling last summer. And I'm going to show you that. So the modeling they had done last year was done with more conventional modeling. And in that modeling, they modeled this ring as a single zone around that ring. And as a result, these holes are spotted basically in the middle. And this is the inner part of the ring, and this is where the 3D inversion was showing the outer part of the ring. And I just put a slice through that voxel just to show it to you in section. And this hole here, we're showing magnetite on the bottom, and we're showing titanium oxide on the top, which is those are the tracking minerals that they're finding associated with the rare earths in this deposit. And the bottom part of this hole is starting to bite into 8% magnetite and 0.5% titanium oxide. So simple exploration example of how we've done how the 3D modeling has just helped improve the picture in this case. Okay, I'm going to sort of shake you up a little bit with this one. Completely different thing for you all to think about, us all to think about, based on the world exploration trends last year. Each of us in this room are spending $1.4 million in exploration. The total amount that we spent on exploration last year was $18.5 billion. You divide that by all the geoscientists working on it, this is how much each of us is spending. We all know we have a problem in exploration that the world needs resources. We don't have enough of them. The world is growing. We all know the China, India, BRIC stuff. And we're not able to keep up with the supply of exploration, or the supply of mines. And so we just have to do a better job. And we believe a big part of doing a better job is for us as explorers being more efficient. We can't be spending 3 weeks on a project that we should be able to do in 2 days. And for us, that's really the story of what the cloud is giving us. It's giving us big supercomputers that we can use just to be more efficient and make better, quicker decisions about what we're doing in exploration. Of course, we put VOXI in the cloud for exactly that reason, so you can access it and use it faster and better, make a better job of it. Also, the science is solid behind it, so that you're getting good answers from it. And something I alluded to in the first slide was about knowledge sharing. We are actually pretty excited about what we can start to do as explorers as we also get more comfortable connecting to the cloud so that we can start to share information among ourselves, share experience, start to learn from each other. And one of the things we will be doing with VOXI is a lot more with an online forum where we can go to share with each other how to do a better job with Earth modeling, compare good examples, bad examples, and just get better at this. So we're quite bullish on what we can do with the cloud going forward, and happy with with where we're going with VOXI. Sorry, I meant to bring this up. Back up a bit. One of the points I'm making here is with the knowledge sharing. One way to learn is guys like me standing up here, or men and women like me, telling you, teaching you things, and we don't have time for questions. So I will have time. I still got a green light. But this. As we get into cloud learning, we're going to be much more peer-to-peer. When you start to connect on the internet and get more comfortable connecting on the internet, we have a much better acceleration of learning as we are able to talk to each other. So, anyway, with that, I thank you for your attention. Oh, sorry, important acknowledgements. This was actually a really big project at Geosoft, so I do want to acknowledge people on the team. Some 25 people were involved in this development. They're all listed here. They're really led by some of the vision of Rob Ellis when he joined us 3 years ago, so Rob's a big part of that. We also could not have done this without the collaborators that we worked with to make the technology real. And so notably, Ivanhoe Mine's been a big supporter of us with Barry DeVette and a number of the names you see there. So thank you to them, and thank you all for listening.
We have time for a few quick questions. Let me summarize. That means the time indicated
Yeah, they actually give it to the cloud directly. They don't have to give it to us, but yes.
So if they are saying that the cloud box or some old thing, is that right? They have to pay you a fee?
Yeah, when you run VOXI, you can either have a subscription to use it, or you will pay per use. When you click that green button, will come up and say, "This is how much it'll cost."
Well, I have to do it at a time and get up to Geosoft VOXI.
Yes.
And push a button.
Yep. You got it. It's not instantaneous. That model I ran, by the way, was 4 minutes. So performance, since I made a point of it, is important. Somebody, I think Laurie was giving me an example. He's an early user of this. You ran a model that ran in 4.5 hours with the technology you're using now. And then he ran it in VOXI, the same model, exactly the same data set, took less than a minute. That's the performance difference of using the cloud. Yes, Yenta. Again, Pat asked if it's just a supercomputer, does it have databases? It really is, we just use the cores. So we scale the problem by cores. The only thing we're interested in are the cores. So we use our own data models, etc.
Very good questions. Did you ask those people ask those questions?
No. Although, I'd love to hear what Joel has to ask.
Sure, Ian. I guess I'm just wondering what tools you're providing to allow the user to assess the quality of the inversion.
Well, the one tool is the forum. So hopefully that's what I meant about the learning, is we have to learn to get better at these things. So that's one tool. The other tools are just the Oasis Montage toolkit, where you can then use that to integrate with drilling and other data sets to improve that. Beyond that, right now, no. But I do expect that this is going to evolve as we start to gain more and more experience as a community.